Bismillah ar-Rahman ar-Rahim. Theta is in the open interval from 0 to 2 pi. We have an integral parameterized by theta. Integral of log of minus log x over x squared minus 2x cosine theta plus 1. X is between 0 and 1. The first step is to note that the denominator can be written as the magnitude squared of 1 minus e to the I theta x. This magnitude squared is 1 minus e to the I theta x times 1 minus e to the minus I theta x. This is 1 plus x squared minus x e to the I theta plus e to the minus I theta. This is 2 cosine theta. The magnitude of e to the I theta is equal to 1. X is in the open interval from 0 to 1. 1 over 1 minus e to the I theta x can be written as summation k from 0 to infinity e to the I theta times x all to the power k. But we have magnitude squared. This is a double sum, summation k from 0 to infinity, m from 0 to infinity. Then we have this multiplied by the complex conjugate with k replaced by m. So we multiply by e to the minus I m theta x to the power m. Can we write this double sum as a single sum? Equate the double sum to summation n from 0 to infinity cn x to the power n. We try to find cn so that we have equality here. On the right hand side, the coefficient of x to the power n is cn. On the left hand side, the coefficient of x to the power n is summation k from 0 to infinity, summation m from 0 to infinity, e to the I theta k minus m. A plus m is equal to n. We can use this constraint to obtain a single sum. We use this constraint to write m as n minus k. K minus m becomes k minus n minus k. That's 2k minus n. Note that k is a non-negative integer, m is a non-negative integer, their sum is equal to n. This means that the maximum possible value for k is n. The coefficient cn is given by the finite sum k from 0 to n, e to the I theta times 2k minus n. We can take e to the minus I n theta as a common factor. Then we have a finite geometric series. We have n plus 1 terms in this summation. If we apply the formula for the geometric series, we have 1 minus e to the I 2 theta, and then here we have the number of terms, divided by 1 minus e to the I 2 theta. From the beginning, we are excluding the case in which theta is equal to 0 or theta is equal to 2 pi. But we also have a problem if theta is equal to pi. This makes the denominator equal to 0. So we will exclude this value. The formula that we get for I of theta will not be valid for theta equal pi. But as we will see later, we can use limits to get the value of I of pi. Multiply by e to the minus I theta over e to the minus I theta. In the denominator, we get e to the minus I theta minus e to the I theta, and this is minus 2i sine theta. In the numerator, we also have e to the minus I n theta. These two exponentials together give us e to the minus I theta times n plus 1. If we multiply by 1 minus e to the I 2 theta n plus 1, we get e to the minus I theta n plus 1 minus e to the I theta n plus 1. This is equal to minus 2i sine n plus 1 theta, minus 2i in the numerator, minus 2i in the denominator. These terms go away, and we are left with this ratio of signs. Sine theta times n plus 1 divided by sine theta. This is the coefficient c of n. To summarize what we did, the denominator was written as the magnitude squared of 1 minus e to the I theta x. Then we used this expansion, but we have magnitude squared. We got a double sum. We were able to rewrite this double sum as a single sum, summation n from 0 to infinity cn x to the power n, where cn is given by this ratio of signs. Now we take this summation, insert it back into the integral, and let's do the integration term by term. We now have to evaluate this integral from 0 to 1 of x to the power n log of minus log x. We make use of the gamma function. The integral from 0 to infinity t to the s minus 1 e to the minus t times alpha plus 1 is gamma of s divided by alpha plus 1 to the power s. Differentiating both sides with respect to s, on the left hand side, we get the first derivative of the gamma function divided by alpha plus 1 to the s. Then we have the gamma function multiplied by the derivative of e to the minus s log alpha plus 1. And the derivative is minus log alpha plus 1 times the exponential, which can be written back as 1 over alpha plus 1 to the power s. On the right hand side, we do differentiation under the integral sign. The limits of integration do not depend on s, but the integrand has this t to the s minus 1, which is e to the s minus 1 log t. When we differentiate with respect to s, we get the same exponential, which is t to the s minus 1. we get the extra term log t. We can do change of variables, z equal to e to the minus t. T is minus log z, dt is minus dz over z. When t tends to 0, z tends to 1. When t tends to infinity, z tends to 0. We can use this minus sign to have our integral with respect to z from 0 to 1. This exponential becomes z to the alpha plus 1. This t is replaced by minus log z, and log t becomes log of minus log z. Recall that we are interested in this integral here. The way to go is to use this identity with s equal to 1. If s is 1, this term is equal to 1, and we have on the right hand side the integral of log of minus log z times z to the power alpha. What about the left hand side? If s is set to 1, gamma of 1 is 1. This part here becomes minus log alpha plus 1 divided by alpha plus 1. To finish this part off, we need to find the first derivative of the gamma function evaluated at 1. Gamma of s is the integral from 0 to infinity, t to the s minus 1 e to the minus t dt. Differentiating both sides with respect to s, we get the first derivative of the gamma function equal to the integral from 0 to infinity, t to the s minus 1 log t e to the minus t dt. If s is 1, then we have this integral here, which is equal to minus gamma, the Euler-Mascheroni constant. The first derivative of the gamma function at 1 is equal to minus gamma. In our case, this integral of x to the power n times log of minus log x is minus. In the numerator, we have gamma plus log n plus 1. In the denominator, we have n plus 1. We have no more integrals. Our integral of interest I of theta now is given in terms of this infinite sum. Minus sine n plus 1 theta over sine theta. Then this term here, gamma plus log n plus 1 over n plus 1. If we replace n by n minus 1, we get a summation from 1 to infinity, and we can rewrite n plus 1 as n. Now we make use of the Fourier series of the logarithm of the gamma function. Log gamma of z, where z is between 0 and 1, is given by these terms and this summation here. Note that we are making use of the logarithm of the gamma function for the particular reason that this Fourier series has a summation that looks very much like the summation that we have for I of theta. Let's match these two sums. I of theta has n theta, and here we have 2 pi n z. It seems like a good idea if we replace z by theta over 2 pi. In this case, we get sine of n theta. This expression is valid for z between 0 and 1. If z is replaced by theta over 2 pi, then theta must be between 0 and 2 pi, and we have this condition from the very beginning. To go from here to there, we just put z equal to theta over 2 pi on the left and right hand sides. We have now a summation that is like this sum if we take this part here, log n over n times the sine. Here it is exactly. But we also have a summation of sine n theta over n without the log n. And this sum is also a Fourier series. It is the Fourier series of this periodic function with period 1. This function specifically is 1/2 minus x when x is between 0 and 1. This is an odd function, so its Fourier series is summation n from 1 to infinity, coefficients times sine 2 pi n over the period, so that's n over 1 times x. And using the formula for the coefficients, we have an integral which can be done using integration by parts. The coefficients are 1 over by n. Like what we did here, replace x on both sides by theta over 2 pi. We get that 1/2 minus theta over 2 pi is summation n from 1 to infinity sine n theta over by n. The sum in the expression for I of theta can be split into two sums. One of them is minus 1 over sine theta times gamma summation n from 1 to infinity sine n theta over n. This summation here is this one after multiplying both sides by pi. We also have minus 1 over sine theta summation n from 1 to infinity log n over n times sine n theta. And this summation here can be written down in terms of the logarithm of the gamma function and these other terms. Here is the expression for I of theta. Recall that theta is in the open interval between 0 and 2 pi, and there was a step in the derivation in which it was a must to assume that theta is not equal to pi so that we don't divide by 0. And this is clear from the expression. We have sine theta in the denominator, and this is 0 if theta is equal to pi. As we will do shortly, we obtain I of pi using limits. Before doing that, we can manipulate the expression for I of theta. One thing that can be done is to use the reflection rule for the gamma function. So we have gamma of z, gamma 1 minus z, is equal to pi over sine by z. If z is replaced by theta over 2 pi, we have gamma of theta over 2 pi times gamma of 1 minus theta over 2 pi is equal to pi over sine theta over 2. This means that sine theta over 2 is equal to pi divided by the product of the two gamma functions. Log sine theta over 2 is equal to log pi minus log gamma of theta over 2 pi minus log gamma of 1 minus theta over 2 pi. We can use this expression here to rewrite this term and get two gamma functions, one of them evaluated at theta over 2 pi and the other evaluated at 1 minus theta over 2 pi. The first special case, what if theta is equal to pi over 2? Recall that in the denominator we had 1 minus 2x cosine theta plus x squared. If theta is pi over 2, this term is equal to 0, and we have 1 plus x squared in the denominator. So what is this integral here? I of pi over 2. We just put theta equal to pi over 2 on the right-hand side. This term becomes gamma of 1/4. This term becomes gamma of 3/4. This factor is 1/2. We can combine the three logarithms like this. Note that this integral can appear in a number of ways. This is the form that we have tackled in this video, but for instance, if minus log x is replaced by y, which means that x is equal to e to the minus y, when x tends to 0, y tends to plus infinity. When x tends to 1, y tends to 0. Dx is minus e to the minus y dy. In the denominator, we get 1 plus e to the minus 2y. Multiplying upstairs and downstairs by e to the y, we get this integral here. That's exactly I of pi over 2 in another form. E to the y plus e to the minus y is 2 times the hyperbolic cosine of y. 1 over the hyperbolic cosine is the hyperbolic secant function applied to y. Our integral of interest evaluated at pi over 2 can also have another form if we use another substitution. If 1 over x is replaced by the tangent of z, minus log x is log 1 over x. So we get log of log tan z. When x is 1, z is pi over 4. When x tends to 0, z tends to pi over 2. The other terms cancel and the integrand is log of tan z. All these guys have the exact same value. What about I of pi? Now we need to take the limit. Note that if we go to the original formula, if theta is replaced by pi, cosine pi is minus 1, and what we have in the denominator is 1 plus 2x plus x squared. That's 1 plus x all squared. Rather than doing things from scratch, we can just rely on the fact that I of theta is continuous in theta. We can obtain the value of I of pi by taking the limit of this expression here as theta tends to pi. Multiply and divide by theta minus pi. What is this limit here? If theta is pi, we have 0 over 0. Let's apply L'Hopital. When we apply L'Hopital, we get 1 in the numerator and cosine theta in the denominator. So this is equal to minus 1. Then we have the limit as theta tends to pi of this bracket divided by theta minus pi. If theta is set equal to pi, we have 0 in the denominator. In the numerator, we have log of gamma of 1/2 minus log of gamma of 1/2 plus 0. So we also have 0 in the numerator. We are in a 0 over 0 situation. We can use L'Hopital's rule to resolve the issue. The derivative of the denominator is 1. The derivative of the numerator, from this term, we get minus log 2 pi over pi. We need to differentiate the logarithm of the gamma function. This is the digamma function. We also need to apply the chain rule. So this digamma function is multiplied by minus 1 over 2 pi. Then we have a minus sign. And the digamma function that we have when we differentiate this term must have the outside factor 1 over 2 pi. When theta is set equal to pi, we get the digamma function of 1/2. This is the limit. Since the argument of the digamma function is a rational number, then we can use the digamma theorem, which allows us to evaluate the digamma function when its argument is a rational number. If p is equal to 1 and q is equal to 2, this summation here is equal to 0, and we just have minus small gamma, the Euler-Mascheroni constant, minus log 2 times the denominator. Our case is 1 over 2, so this is 2 times 2. Then we have minus pi over 2, the cotangent of pi times the fraction. Cotangent pi over 2 is equal to 0. Psi of 1/2 is minus gamma minus log 4. The value of I of pi is this quantity divided by 2, so minus gamma over 2 minus 1/2 log 4. Then let's not forget this term here. These two logarithms can be combined as 1/2 log pi over 2. I of pi, which is this integral, is minus Euler's constant over 2 plus 1/2 times log pi over 2. Another special case, if theta is equal to pi over 3, cosine pi over 3 is equal to 1/2. So the denominator is 1 minus x plus x squared. There is no problem now in using the general form. We can just put theta equal to pi over 3, and we get an expression that involves gamma of 1 over 6 and gamma over 5 over 6. We can keep both, or we can use the reflection rule to write everything, say, in terms of gamma of 1/6.